If y was directly proportional to x, we could write that like this. Now essentially that means if we double x, then we also double y. If we half y, then we half x. So it has the same effect on both, but only when we're scaling it by a certain factor. Like if we added 1, that's not necessarily going to add 1 to x. And we could convert this into an equation if we wanted to. So y equals to x, that works, because if y is 2, then x is 2. And if I double y, that becomes 4, that becomes 4. So that seems to work. And then if I times x by 2, let's see what effect that has. So this time y is equal to 2x. Now this actually keeps the proportion, because if x is equal to 1, then y is equal to 2. And if I double x to get 2, then y also doubles. That keeps the proportion. Now it doesn't really matter what I do to this x here, as long as I'm timesing and dividing. So if no matter what I do here, I can times that by as much as I want. And it's still going to be proportional. Now, timesing by 2 dividing by 3, that's basically timesing by 2 over 3. But let's see what happens as soon as I add something. So if I added 1 to this, does this still work? So if x is equal to 1, then y is equal to 3. Let's see what happens if I double x to 2. 2 times 2 is 4, add 1 is 5. That's no longer doubled. It's increased by 2, and that's because it's in the form of y equals mx plus c. The gradient is 2, it's going to go up 2 every time I increase x by 1. But it's no longer proportional. If we add or subtract anything, then it's not going to keep its proportionality. So this leads to the conclusion that we can basically have y is equal to something times by x. And it works exactly the same way as if I put x squared there, or x cubed, or root of x, or anything in terms of x on this side. And I can actually rearrange this and find k if we wanted to, by substituting in some values which we know. But we can't for this example because it's inversely proportional to the square of x, not directly proportional. That's different. Looking into graphically, if something is directly proportional, then it's going through the origin. It's doing something like this. This is our graph of y equals x. And you can change the gradient, essentially. So if you're timesing or dividing x, then that's basically what we're doing. But if we add something, it's no longer going through the origin. It's crossing at a higher point. That's why it's no longer directly proportional. If it's the square of x, it's doing something like this, or the root of x, something like that. And again, if we added a thing to that, it's not going to be proportional anymore. But if it's inversely, then the inverse means 1 over. So this is actually going to be that y is directly proportional to 1 over x squared. That's what that's telling us here. Let's think about what effect that has. So if y was directly proportional to x squared, we could test this with an equation. Y is equal to x squared. And we can see what happens if we double x. And it has a square effect. If we double x, then it's going to times y by 2 squared, or times it by 4. And if I times y by 2, then it's going to have the square root effect on x. So x would be times by the root 2. If we've got an inverse proportion relationship, as one gets bigger, the other one gets smaller. So in this case here, if I was to times x by 3, I'm actually going to divide by 9 times the amount. And we can see that here, but from 1 up to 3, I've divided by 9. And from 1 to 4, I've divided by 16, which is 4 squared. So that relationship does seem to be working. But we want an equation for this. And to do that, I can replace the proportional with equals to k over x squared. Now I've essentially times 1 over x squared by k, but I've just moved this to a numerator. Now k is something we want to find, so I can put k is equal to y times x squared, because I want to undo that dividing by x squared. I do the same to both sides, which is multiplying to undo that. And now I can substitute in some of the values which I know. And I'm going to pick one of the easy ones. It doesn't actually matter which one we pick, but I'm going to pick that y is 9 and x is 1. 9 times 1 squared, that gives us 9. So I can go back to my equation and I can replace k with 9. Now just to see if this works, 9 divided by 1 squared does give us 9. 9 divided by 3 squared is 9 divided by 9, which is 1. And you could check for the other ones as well, but they're not so friendly. So this is our equation for y in terms of x. In terms of x, because it has x on the other side. To find the value of x when y is equal to 16, we can simply use this equation here and rearrange it so that x is the subject. So I'm going to times by x squared to get yx squared equals to 9. Then I'm going to divide by y. And then I'm going to undo the square. The opposite of that is square root. So I get that x is equal to square root of 9 over y, and y is equal to 16. When we do it square rooting a fraction, we can square root the numerator and the denominator separately. And we get that x is 3 over 4. Now, another way of going about this is if we understand what the proportion is basically telling us. Our y value here was 1. If we times 1 by 16, we get 16. And it's going to have the opposite square root effect on x. So we're going to divide by 4. And that's basically what we have down here, 3 divided by 4.